Where were we? Talking about Chapter 3 in maps. And we will specialize that to linear maps. There are nonlinear maps that you could have, and hopefully it will be clear from today's lecture the properties of what it takes to be a linear map. Some examples: we will actually create a vector space from a set of linear maps. That's maybe this abstract notion that is more than just a matrix. And then we will start talking about different subspaces associated with linear maps. This we will define. T is a linear map, and it's a linear map going from a vector space V into another vector space W. We will try to get into some particular subspaces, one being the null space. I don't know if we will get as far as the range space. And we'll talk about those maybe in more general terms than what you're used to seeing. Which is Chapter 3. Is a function, and I sort of like to graphic some kind of a picture. You could think of some vector space V and another vector space W, and now we are interested in this map, linear map T, between those two vector spaces. A linear map is a function that takes as its input an element of, let's say, vector space V, and uniquely identifies an element of vector space W. The notation that we will use will vary, but we might say T, which is the map T, is going to then map between V and W, where this now means from vector space V to vector space W. To be a linear map actually requires two properties. First, we have to have additivity. Which means that if we have this map T and it operates on the sum of two vectors in your vector space, then that's equal to TU plus TV for any U and V in the domain vector space V. So it needs to have this additivity property. It also has to have a homogeneity property. For all scalars F and V in our vector space. If our map has these two properties, then it will be a linear map. And we need both of those. Together, these properties make a map linear. And just to make the same comment that's made in the textbook, sometimes we mix the notation. By that, I mean we might say T of argument V, or we may simply say T operating on V, and that means the same thing. That notation may get blurry. We may use either or both interchangeably. The other notation that we will use is we will say the linear map, or the set of linear maps, or L, script L of V comma W, is defined to be the set of all maps T such that V is taken into W. And this linear map is an extremely broad category, although it doesn't encompass everything. It has to have those two properties, additivity and homogeneity. Let's look at some examples that are used in the book. Again, just to keep track of what we're doing, we started with vector spaces. That is what we were playing with in chapters 1 and 2. Now we want to map between vector spaces, and they may not always be the same vector space that we begin in and what we end up in. So don't think that you're always mapping from one vector space into an identical vector space. It could be different domain and codomain. One map is the zero map, which maps all elements of the vector space V to the additive identity in the vector space W. Meaning now we could have 0V equals 0, and now that 0 is overloaded. This is a map, and this 0 is actually the additive identity in vector space W. Again, we have that piece of information that you need to keep track of. This notation of using 0 to represent many different things, you could think of it as overloaded. The notation is overloaded. Which is another way of saying that the same symbol, which is this 0 symbol, may mean a map, it may mean a vector. You just have to sort of know from the context what it means. Pardon? And a scalar, correct. It could be a scalar in our field of numbers. So the same symbol means several things. And hopefully it's clear from the context. We said examples. That was one example, the zero map. Let's look at some more. That one wasn't too difficult to think about other than the overloaded notation. We could have the identity map. This actually maps each element in the vector space V actually back to itself in V, in the vector space V. There, the domain and the codomain are the same. Here we might say I is an element of all the linear maps from V to V, which really says it's from V to V, and we might denote that as IV is equal to V. And that's a linear map, the identity map. What are some that are not so maybe still matrix type? What about the differentiation map? Suppose T was this linear map that's differentiation, meaning that's now this linear map from the set of all polynomials over the field of reals taken into the set of all polynomials in the field of reals. And we might say, oh, P of X is now some polynomial, and T now says that we take TP, and that's really just the derivative of P. As an example, just so that you're thinking about a concrete entity, suppose we had some polynomial 3x squared plus 2x plus 7. If we now said, oh, operate on that element in a vector space, the vector space being the set of all polynomials over the set of real numbers, or the field of real numbers, and maybe P is now 3x squared plus 2x plus 7. What's TP in this particular case? We still remember our first semester calculus, right? 6x plus 2. That would be TP for the differentiation operator. That's what we're meaning. Yes? So this, I maybe stopped you too soon. You said your question was, this looks like the identity map. And is that your question? So the vector spaces in this associated with this linear map are the same, meaning it's going from V to V, where V is this set of polynomials of whatever order you want it to be, infinite dimensional, and so is the output. That's all that's meaning. That's meaning that you could start with a 10th order polynomial that's going to map into a 9th order polynomial. Yes, so now you have to, so that's a good question. Given this form, T is an element of L of P of R, comma, P of R. It really doesn't tell you anything, does it? You really don't know what T is. T could be a multiplication by x squared, and it would fit into that. And that's one of the examples in the book. Here we say T is a differentiation operator. So that's, in a sense, you need to understand it by the context of whatever you explain T to be. Is that clear? So just the statement is too vague to tell you anything. You have to be told, and I guess I did in the line above, this is the differentiation operator. So that's getting you to think, oh, if I have a polynomial in x of any order, I can differentiate it. And that's going to map from this vector space of any order polynomial into itself. That's all that's saying. But t, you had to be told what it was. You could have said, oh, t is something else, and let's do that just in a minute. But now let's check to make sure that this is okay as far as, is t a linear operator? And that's this script L. So that script L is telling you this is supposed to be belonging to a linear operator. What does it have to possess for this linear operator of differentiation for it to be linear? Two properties, right? Additivity and homogeneity. If we wanted to check this as far as whether it satisfied those properties, we could say, oh, if I give you a sum of two polynomials taken from script P of R, and those I didn't say what they were, they're just generic P and Q, and now if I differentiate those, which is what it would be if I said T of P plus Q, so this is actually, maybe I should have snuck that in, this is now T of P plus Q is equal to P plus Q derivative. That's equal to P prime plus Q prime, which is TP plus TQ. Oh, good. Additivity is satisfied. Is that okay? From basically the definition of derivative. The derivative operation for polynomials satisfies the sum derivative is equal to the derivative of the sums. And that allows you to say that this linear operator T does satisfy this additivity property. What about homogeneity? Now we could say, oh, we need T of A, we need T of AQ or AP. What would that look like? That's now AP prime. But if A is just a scalar in our field of numbers, let's say the reals, that doesn't influence the derivative. We now have A P prime. Maybe I should make that very clear. And that's now equal to A T of P. And so it does satisfy the homogeneity property. The differentiation operator, which you can't tell from just that one line, you have to be told, what is this linear operator? Oh, it's the differentiation operator. Oh, it's a linear operator. What are some others? We're scaffolding. We're going back and picking up stuff you already know. We just did in differentiation the first semester of calculus. Now let's go into the second semester of calculus with integration. Are these linear maps? And you could actually talk about two different kinds of integration. You have indefinite and definite integration, and those have different vector space for the domain and the codomain. Meaning, if I now wanted to do an indefinite integral, and let's say I now have the linear map T, my domain, where I pull my vectors from that T will operate on, is the set of all polynomials with real coefficients. What's the codomain? What's the output of that operation? The indefinite integral. the same, isn't it? It's the same vector space. That's P of R. Now, contrast that with a definite integral. Suppose we, again, start with a vector space of any polynomial. What's going to be the resulting vector space that we land in if we're doing a linear operator of integration in a definite sense? Now we have limits on our integral, don't we? Now we'll just end up in the reals, won't we? So our codomain is not this vector space of polynomials, it's actually the reals. Yes? So the ending space, the codomain, the vector space, is going to depend on the linear operator. And that's it. Yeah, it's related to whatever you're doing with your linear operator. And now we've found that we have a zero map, we have the identity map, we have a differentiation map. There's all sorts of linear maps. There's an integration map. There are, let's keep going. There's dimension changing maps, meaning suppose I have a linear operator that goes from R3 to R2. What does that mean? That means that I could take a 3 vector, let's say a point in this room, and now I get to walk around, right? I could say, where is my head in this room? It's in some coordinate. It's at some x, y, z. I said the head, so it'd give a z direction. So now we have an x, y, z, and maybe we want to linearly map that into where I'm standing, just on the floor in the xy plane. So this linear map starts with a vector x, y, z, and now maybe it takes those locations and says, oh, the first coordinate of your resulting vector in R2, let that be 2x minus y plus 3z for whatever reason. So now you give me an x, y, z, and the first coordinate is just going to be a linear combination of those coordinates in your beginning vector. And that will be your first coordinate in your codomains vector. And the second coordinate is now 7x plus 5y minus 6z. And that changes the dimension. You go from 3 space to 2 space because you only have 2 coordinates in your output. They're a function of the initial 3 coordinates in your beginning vector. Projection map. Here, maybe we have a linear map, again, from R3 to R2. Projection, let's say that it takes t of x, y, z, and now it does do what I was saying before. Maybe it just takes my head location in the room and projects that onto the floor. And now wherever I am in the room, or my head, wherever it is, You don't care where it is vertically. You just want to know where am I standing. Projection operator. Or a projection map. And that's a linear map. Is it? Yes. Uh, well, yes. So now we could say, so the question was, don't you need to restrict that? How do I want to say this? Let me correct that by doing the following. That. Okay, so I'm not going to erase my 0. I'm going to go from R3 to R3. Thank you. So the question was, you're inconsistent with your example, and that's the correct question, or you're correct in your question. We stay in R3, but now we've just zeroed out the height coordinate. Now, is this a linear map? Is that unique? For any XYZ, it goes to a unique point. It's maybe not unique in the other direction. You might have many Z's that map to that same unique point in the output. Now, what can we say? Well, if we do a direct proof, for example, for additivity, we could say let U be U1, U2, U3, and let V be V1, V2, V3. T of U plus V is now T of U1 plus V1, U2 plus V2, U3 plus V3. But that's now T operating on that, and we've said that that's now U1 plus V1, U2 plus V2, 0. But we could write that as U1, U2, 0 plus V1, V2, whoops, 0. And that's simply T of U1, U2, U3 plus T of V1, V2, V3, which is T of U plus T of V. And that is at satisfying the additivity property. What about homogeneity? Let's let our scalar alpha be anywhere or belong to any of these fields, R or C, F. Then if we say T of alpha, let's say U, is T of alpha U1, alpha U2, alpha U sub 3. But that's simply alpha U1, alpha U2, 0, which is alpha times U1, U2, 0, which is alpha T of U1, U2, U3, which is alpha T of U. satisfies that, so T is linear. Where T, if you only read the last line, you're going, what do you mean T is linear? T now is that projection operator. You have to know what that T is representing in your example. Having too much fun. Let's do some more. Let's do another map. Let's now do a translation map. So that let's translate, and now we don't need to include as many coordinates to get the idea. Let's just play in R2. Let's play on your desktop in X and Y. So now let's say that T of U1, U2, we have two coordinates. Let's say that that is U1 plus 1 and U sub 2 plus 2. Is the translation map linear? And what does it take, or what might it take, to show that it's not linear? Just one counterexample, right? Let's guess it's not linear and see if we can come up with a counterexample. And I'm going to just show you the counterexample, and then we'll try to justify or explain why that's okay to use as a counterexample. The answer is no. It's not a linear map. The counterexample is to ask the question, is the additive identity, and what is that? Well, that's just the zero vector. Is the additive identity mapped onto itself? And if it's not, then it's not a linear map. So this would be a nice counterexample. You could quickly look at your map in question and say, is it linear? And then you could say, well, okay, it does. It does take the zero vector and maps it into the zero vector. Okay, that's not a counterexample. But if it doesn't, then you can say, oh, it's not a linear map. And we'll explain that in a minute, but let's just look at what happens to this translation map that we have. Suppose now we say, okay, take T and operate on the zero vector. So we plug in U1 of 0 and U2 of 0. And what do we get as an output? 1, 2. We get those constants, 1 and 2, and that doesn't look like the zero vector, does it? That's not equal to 0, 0, which is the zero vector. Which is really just another way of saying it does not satisfy homogeneity for a particular, let's say, value of scalar alpha. So here's the explanation. for y, a linear map should map the additive identity onto itself. From homogeneity, we have T of alpha V is equal to what? The homogeneity property says T of alpha V should be alpha T of V. Now, if you remember all of your propositions, you don't have that many yet. You just have up through chapter 2, and we're starting in chapter 3. So let's go back to chapter 1 and recall proposition 1.4. That was an overloaded use of the zero. We have 0v, a scalar, 0 times a vector, equals what? A zero vector. That's proposition 1.4. Now let's use that. Let's go ahead and, for this case, let's let our scalar A be the zero scalar in our field. And let's let V be any element in our domain vector space, capital V. Now, let's play with what we have. We have T of AV, but now we said A was going to be 0, so we have 0 times V. That's equal to T of 0, and here we are using, in the argument, we are using proposition 1.4, right? Proposition 1.4 says a scalar 0 times a vector gives you the 0 vector. So we're just showing that in the argument of T from proposition 1.4. But now the homogeneity property says that T of AV should be A T of V. We know that from homogeneity, that the left side, T of AV, is equal to A T of V for any A, and now we've specialized that to the 0 scalar, A. But that's now equal to what? The 0 scalar times a vector, which you have a vector resulting from T of V, is going to be 0. That's our 0 vector. And if we wanted to, this also is proposition 1.4, isn't it? It's 0 times a vector is equal to the 0 vector. And if we compare some of these terms in this equation that are equal, we have T of 0 is equal to 0. That means that the additive identity needs to map into itself for a linear operator. That was the counterexample that we utilized to show that the translation map was not a linear map. We verified that t of 0 was not equal to 0. So that's a counterexample. That is not a linear map, because a linear map says that the additive identity needs to map onto itself, or t of 0 better be 0 for a linear map. Questions on that? Well, that could be a easy or a quick check on some map to determine whether or not it is a linear map. You say, oh, well, it's got to at least take the 0 vector and map it onto the 0 vector. If it doesn't do that, then I know it's not a linear map. What about some other maps that we can talk about? What about norms? And are they linear? We haven't discussed norms yet. Which are useful for sort of discussing lengths. We haven't talked about lengths of vectors. We'll talk about that later, but we'll just define them now and see if they are linear. Let's now take a vector, x, and let's give it n coordinates, x sub 1, x sub 2, up to x sub n. And each of those coordinates belong to this field of f, either R or C. Let's just define some different norms. And we'll play with them later. Has everyone heard of the 1-1? No, not the 1-1, but the 1 norm. I'm giving this, I'm going to cause this 1 note to go into fits. Not 1 note, but 1 norm. The 1 norm of a vector. Suppose that you now have a vector. Norms are typically 2 vertical bars around your vector of interest. The 1 norm is indicated, let's say, by a subscript of 1. This is now defined as we take each coordinate's absolute value, raise it to the first power, and take the first root of the sum. So it's now the absolute value of x1 plus the absolute value of x1 plus the absolute value of x3 up to absolute value of x sub n. Or that's now this sum of absolute values of each coordinate in the vector x. That's the 1 norm. That one maybe you aren't that familiar with. Maybe you are. Has everyone seen the 1 norm? And these just are different ways of measuring length of a vector. Okay? So let's now look at the 2 norm. This one is maybe what you're more familiar with. This is the Euclidean norm. But the reason why I made such a big deal about how I was defining the 1 norm is the 2 norm is similarly defined. Question? Yes, I mean x sub I to the 1, and that's implied by not raising it to a power. But I could put that right here, but I didn't. So that's just the absolute value of each coordinate. Question? So now x, think of x as just a normal vector. Let's play with the reals. So now if you had a 3 vector, let's say that you had x, y, and z in a 3 vector. Now you just take the absolute value of x plus the absolute value of y plus the absolute value of z. That's the one norm of a generic x, which is now x sub 1, x sub 2, and x sub 3. So now you could draw x from, oh, yes, so this is now a particular x in that set. So I'm just saying x, any x is going to have this functional or this form where all the coordinates are coming from, let's say, the set of reals or the set of complex numbers. Now, in this case, in the one norm, you pick a specific x, but if you don't even, if you just say in general x, then you take the first coordinate, take its absolute value. You take the second coordinate, and then this is general in terms of whatever you've specialized your dimension to be, or how many coordinates you have. Now, the 2 norm. Now we take the absolute value of the first coordinate and square it. Second coordinate squared. And we do that for all the coordinates. And then we actually raise it to the 1/2 power. And the 3 norm is the coordinate cubed plus the second coordinate cubed raised to the 1/3 power, etc. Or you could write this now as the square root of this sum from I equal 1 to n of x sub I squared. That's the 2 norm, the Euclidean norm. Now I just suggested we maybe have the 3 norm, but let's just go to the limit. The infinity norm. Can you guess what that is? If you use this same strategy, you take each coordinate and you raise it to a power, whatever your norm is. Let's say it's the 100th norm. You would take the first coordinate and raise it to the 100th power. Take the second coordinate and raise it to the 100th power, and then you would take the sum of those and take the 100th root of that sum. Do you see what might happen as you let that norm get bigger and bigger as far as now the infinity norm? You're taking each coordinate and raising it to a very large power. What happens to the result? Well, you're really going to just isolate on the coordinates that's the biggest. So the infinity norm is really just going to say, oh, this is going to result in taking the max over all I of the absolute value of the ith coordinate. That's the infinity norm. So there are 3 different norms. We didn't need all of those. We're going to simply look at the 2 norm and ask, is it linear? Is the 2 norm linear? So now we have t, let's say as a map, is going to produce the 2 norm. What are we starting with? Let's just use an example. Suppose we start with a 2-dimensional vector. What's the norm going to give us? What's the output? Just a real number, isn't it? It's now going to go from R2 to the reals. So now think of the xy plane. You take any point in that plane and you calculate the distance from that point to the origin. That's the 2 norm of a two-dimensional vector. Is that a linear map? Linear or not? If my pen would respond, it's not a linear map. So now it's not additive, is it? So now if we look at the y for this, we need a counterexample. And we only need one, don't we? We don't have to show that everything doesn't satisfy this additive identity. All we have to do is really pick one example. And one such example might be, suppose we let x equal 1 minus 1 and y. So now I'm using x and y differently. X is x sub 1, x sub 2, its coordinates. Y is y sub 1, y sub 2. Suppose y is 1, 1. Now in this particular case, if you add x and y together, you get 2, 0. And what's the 2 norm of a point 2, 0? 2. You just go to that point. That's in the x direction, let's say, or in the horizontal direction. What happens if you take the 2 norm of x? That's the square root of 2, isn't it? What's the 2 norm of y? Square root of 2. So now is 2 equal to 2 times the square root of 2? No. So there's our violation. Additivity is violated. Wow, this is starting to get interesting. I hope that maybe you're not paying attention, but I'm starting to get frustrated. But that aside, let's look at an interesting case. An interesting development is that we can turn the set of linear maps, which we are calling L script L of, let's say, VW, into a vector space itself. What do we mean by that? Well, this is now creating an abstract space. guess it's wanting me to slow down, and I'm not going very fast. This fact is an example of an abstract space. So what do we start with? We have a set of vectors and the elements and those vectors are actually the elements wow of the set of linear maps L from V to W. Those are our elements. Now, to be a vector space, what do we need? We need those to be together with a set of scalars. So we need these vectors and a set of scalars. And let's let that just come from F, which could be R or C. I knew when I started, and it started to give me weird behavior, that I was in for a long afternoon or early evening. Now, in addition to vectors and scalars, if this is going to be a vector space, what needs to happen? We need to have two binary operations, don't we? We have to have addition, vector addition, and scalar multiplication. So we need our two binary functions, let's say plus and multiplication, where this plus is our vector addition, and this multiplication is our scalar multiplication. Now, to show that this is a vector space, we have, let's say, for S and T that are both vectors in this set of linear operators from V to W, we can define S plus T to also belong to this set of linear operators from V to W. Where in this case we have S plus T operating on some vector V is equal to SV plus TV, and that's true for all V in our vector space. That's the vector addition that we need. We can also have our scalar multiplication And that says then that that could be property 2. For alpha, a member of our fields, R or C, then we have alpha T is L of VW, where alpha T operating on V is equal to alpha times TV, which now allows us to say that if we wanted to, we could actually have a vector space composed of these linear operators. So these linear operators actually are vector spaces. And then we would have to worry about maybe going into chapter 3 with a mapping between these vector spaces, whatever that means. But we could define a vector space to be, or to consist of, elements or vectors being linear maps. That could create a vector space. So that satisfies all the properties of a vector space. Now, can I give you a question? The question is, what is the additive identity of the vector space of all linear operators V to W? So now if you're thinking about that, while the computer is thinking, think about what is the additive identity in your set or in your vector space of LVW. That's the question. So now what is it? It's going to be the zero map, isn't it? Did everybody see that? It was zeroed out completely. Everything is zeroed out. We've now mapped that So this was the question I was trying to ask when I was so rudely interrupted. What is the additive identity of the vector space L of VW? And you've already been answering that and waiting for me to write it down. The answer is the zero map. And that's the additive identity in that vector space. And a vector space has to do what? Has to contain an additive identity and it has to have additivity and homogeneity. Or a vector space has to be closed under addition and closed under scalar multiplication, which you can subsequently show. Now, you can actually, with some of these linear maps, you can actually concatenate those or compose those. For some pairs of linear maps, we can even define multiplication of linear maps. What do I mean by that? Suppose that we're given two different linear maps. T that maps from U to V, and suppose that S is a linear map from V to W. Then for some maps, we could actually say the map ST is going to be between what? It's going to start with U, isn't it? That's where T begins its domain. It then goes into a codomain of V. Then S takes that as its domain and maps the result into W. So ST is going to be this linear map from U to W, where you could think of this as saying, oh, ST on V is equal to S on TV. And this really only works when the output space of T is the input space of S, or for S. Now, what do we know about this set of operations, or this multiplication of linear operators? It's not necessarily commutative, is it? ST is not necessarily equal to TS. And I think in the book they give an example of that, where maybe the first operator, T, is the differentiation operator, and S might be the multiplication by x squared. And you can see that those are not going to be equal. ST is not going to equal TS. It really sort of depends on when you differentiate and when you scale or multiply by x squared. Now, as a precursor to where we are going, we need to get into concepts dealing with these operators. And one such concept is the null space. The null space, this is giving you something to chew on over the weekend. The null space of a linear map is the subset of the input space that maps to the zero vector in the output space. Picture. Suppose this is our input space V, and this is our output space W. We are now mapping between those with this linear map T. But we now want to talk about a null space, or what subset in V will, all points in here will map to the 0 vector. So no matter where we are in this subset, all of those points are going to go to the 0 vector, and this subset is called the null space, or we might call it n of t, or we might call it null of t. We want to know, can we identify for a particular map what this subset represents or looks like? And that's where we're going to go. We're also going to go, where can we get to through this linear map? What's the range? What's the range space? And those two will actually be subspaces, and we'll pick up at that point next time.